Okay, so this is the first lesson of applications of equilibrium, essentially. So we're going to start with solubility equilibrium, and then we'll have another assignment, and then we will do acid-base equilibrium. So what we're going to do is apply all the concepts that we learned in the last section to this. So this will look at applying ice tables to a certain situation. Then we'll do like Le Chatelier's principle, even calculating a trial value or Q and seeing which way the equilibrium will shift, that kind of thing. Okay, so we're going to use all the principles that we have just learned for the next 2 chapters, basically. All right, so solubility we talked about in grade 11. By definition means the amount of solute that can dissolve in the given amount of water at a particular temperature. So if you remember last year, we did things with a solubility curve, and if you change the temperature, then the solubility of a solid increases. We did things with, we did talk about gases, which we're not going to do in grade 12, that gases will decrease when in solubility, which means they come out of solution, like your warm pop becoming less fizzy, that kind of thing. Okay, so the big idea here is the amount. How much is dissolving, which we're also going to call that the molar solubility. Why molar? Because we're going to do ice tables, right? And when we do ice tables, we always want concentration, which is moles per liter or big M. So we're going to, again, keep with those principles that we talked about the last unit. So this, in grade 11, we would have done grams per mole. When sometimes we're not going to do that here. Okay, so last year, another thing you had to do was you had to predict whether something was going to be insoluble or not. So for example, this double displacement reaction given here is silver nitrate, and sodium chloride makes sodium nitrate and silver chloride. That is, and you would have switched the partners, the 2 reactants were aqueous, and then you had to use the solubility table to make silver chloride. So on the back of our periodic table, there is a solubility table, but what we're going to focus on in grade 12 is the situation that we would have said something was insoluble or less than 1 gram per 1 liter of water could dissolve. So tiny, tiny numbers. And now we're going to say, well, can we get the silver chloride to dissolve a little bit? Yes, we can. But it's going to be a very, very tiny amount, like numbers like 7.9 times 10 to the negative 9 and things like that. So if you have preferred not to use scientific notation, then it is going to be important that you won't be able to type those numbers into your calculator. Okay, so last year you had to do the total ionic equation, where you split apart all aqueous substances, and then we had to do net, where you crossed out what we called the spectator ions, and showed the formation of the solid. Which is fine, but what we're going to focus on in grade 12 is the dissociation equation. So in this case here, without doing the total because it's sort of useless, say if we were going to cross out the spectator, sodium or nitrate is aqueous on the reactant side and on the product side, so it crosses out. Sodium, aqueous here, and then so the net ionic equation would show the silver and chloride ion coming together to make silver chloride. But what we need is the dissociation equation. So this red is not on your note if you want to pause the video here and write it down. Okay, so the dissociation equation, again, you have to remember what dissociation means. Which is essentially also the definition of an aqueous solution. You have ions dissolved in water. So what we're going to do is we're going to use the dissociation equation. So in grade 11, we would have said that silver chloride was insoluble. And now we're going to say, well, we can get it to dissolve a little bit, but it is going to exist with reversibility or an equilibrium system. So I'm just going to use the same example up there. So silver chloride is our solid, always the reactant, and then the products are always the ions. So in grade 11, I encouraged you to write the charges, but I said that you had to write the aqueous. So it's very important that we have the aqueous designation, because as you know, when you write an equilibrium law, you don't include solids. So only aqueous and gases, right? So in this section, the fact that the ions are on the product side is going to impact the equilibrium law. Okay, so we have a double arrow here because in the past, we would have said that silver chloride was insoluble. The ions are always the products. Ions do have a charge. And so I do recommend that you put that in. The convention is when we write a formula that the cation goes first. It doesn't really matter because we're going to multiply, right, when we do the equilibrium law. But so whatever's written first is going to be, the metal is going to be the cation, and the nonmetal will be the anion or negative. So that can help you. And then what we're going to do eventually with this equilibrium expression is KSP. So now we have the solubility, and you'll see in a second why it's product, which is the answer to multiplication. So instead of KEQ, because we're specifically talking about a solubility system, then we use the word SP. But it's the same thing, same principle, same products over reactants. So the size of KSP will and favoring one side over the other, all of it is the same. You could really just call it K, but we want to designate that this situation is equilibrium. So you're going to have to write your own expressions like this dissociation equation. So you should remember these two ideas. Solids always on the reactant side, ions are always the products, but I will give you the formula for the solid. You don't have to stress about crisscross rule and all that kind of stuff. Okay? All right. Okay, so silver chloride, last year we would have said was insoluble, but maybe we can get it to dissolve to a slight extent, a tiny amount. I will apologize. The sentence that's on the note, when I was reading it over to make this video, I thought that does not make sense, like even English-wise. So if the red here, like right here, if you want to fix that on your note, I apologize. So equilibrium is established when no more can be dissolved. So there's a couple of ways that you can word these questions. So when no more can be dissolved, that's called a saturated solution, if you remember from grade 11. So unsaturated would mean more could dissolve, and supersaturated is where you have too much or you've got recrystallization. So saturated solution, no more can be dissolved. So if the question talks about a saturated solution, then that means that it is at equilibrium. And why is that important? Because the concentrations in a saturated solution will be used in the E line of the ice table. Okay, so there's one way, saturated solution. And then when we do some of the questions, you can see another way that you could actually be given information about your equilibrium system. Okay, so if we have, back to our dissociation equation, AgCl and Ag and Cl, what's the equilibrium law? Again, we're going to write KSP and products over reactants. Oh, I forgot the charge there. So there are no solids in the equilibrium law. Which is from 7.2's note, if you need to go back and review that. So that means that because when you write a dissociation equation, the solid is always on the left. That means that there, which is the reactant side, then there is never going to be a bottom. So that's why it's called a product, because you're only going to multiply the concentration of the cation and the anion together. There will be two terms. There's always two ions, right? A plus and a minus. Opposites attract. So these are, in a way, these are kind of simpler because there are things about it that will be the same every time. Solid always on the left, a plus ion and a minus ion on the right. Okay. So they should look very similar. All right. So here we're going to do some examples. So it says KQ is KSP because the concentrations are based on molar solubility. So this all, like I said, all the same principles apply, like no solids in the equilibrium law, coefficients or exponents, all the same principles apply. So molar solubility is another way to talk about the maximum amount dissolved. So again, that goes at equilibrium or the I line in your ICE table. Okay, so as far these questions are really sort of, there's not a lot of variety except in their wording. It could talk about saturated solution. It could talk about how much is dissolved at equilibrium, or they could say the maximum amount dissolved, or they could just say molar solubility. Most of the time it'll just talk about molar solubility, but we'll do a variety of questions. Okay, so this first example here just wants us to write the solubility product, which is KSP. Okay, so in A, we have, again, there's always going to be two terms, no matter what. So we have silver ions, and this is chromate. If you struggle with polyatomic ions and remembering polyatomic ions, there is a chart on the back of your periodic table. So again, you know, that information is always given to you. Even if we were going to write a traditional exam at school, you would have that information. So don't try to guess, don't screw yourself up, and then make sure that you are using the tools that you're given. Also, you'll notice that when you do these questions, a lot of it will be silver and iron and lead. These are big ions that generally don't dissolve. Things like the alkali metals, all of those will dissolve. You'll never see one of those in this kind of question because it's never going to be a solid in water. It would always dissolve. So you'll notice similarities with that too. And that is on purpose because things like silver and certain irons and this barium, lead, those are the things that are not generally very soluble. Okay, so that actually does make sense. Okay, so now you do have to be careful. This 2 out front here means that the silver has to have a coefficient of 2. Okay, so when we do the next one, we have barium and chromate, but they're both 2, so there's no coefficient there. And then silver is cubed. And a phosphate. Okay? So calculating the KSP from the solubility data. So again, I've given you the solid here. So go ahead and write your expression because you're going to need it. Okay? The molar solubility of AgBr in pure water is 7.1 times 10 to the negative 7 moles per liter. Okay, so then again, here it says molar solubility. It doesn't say at equilibrium or anything like that. So you do need to remember molar solubility is the maximum amount that can be dissolved. The maximum amount that can be dissolved. Okay, that's a saturated solution. Saturated solution, okay, that's equilibrium. When we do these ice tables, I don't want to say cheating at ice, but we are kind of cheating at ice a little bit. And we're going to kind of cheat at stoich or streamline the stoichiometry process. Okay, so this is going to go here. And similar to the questions from the last section, so it's like you have a solid and then you're trying to dissolve it in water. So originally we don't have any ions, right? Just like the last question. And then you might say to yourself, well, what about silver bromide? What do we have for that initially? But we don't care because it's a solid. We're actually going to cross it out. But we're going to use that molar solubility value. And because these are all have a coefficient of 1, what that means is if silver bromide is 7.1 times 10 to the negative 7, then silver is 7.1 times 10 to the negative 7, and so is bromine. You can certainly do the whole ratio. So we're looking for, let's say, silver. Its coefficient is 1. AgBr is this over 1, right? So because it's all 1, then you're going to get the same value. So now you write the equilibrium law, which you get marks for, just like the last section. You can either write it out like this. Because it's the same, you could have written squared as well. That'll get you the same answer. But you really have to be careful. Again, make sure that you know how to do scientific notation in your calculator. So 7.1 times 10 to the negative 7 times 7.1 times 10 to the negative 7. The KSP value is 5.04 times 10 to the negative 13. Okay, so we're given the molar solubility, which goes in the E line. But we don't really care about the solid. We're going to cross it out. However, we're going to use stoich and sort of cheat to fill in the rest of our ice table. You could also even think of it like the x value. So if it's 0 plus x, then x equals 7.1 times 10 to the negative 7, which is exactly the same as the other section. But like I said, this one is actually in a way a little bit easier because there isn't a lot of difference in how the ice table looks. So even something like this one, the molar solubility you're given for silver chromate. So the 2 becomes the coefficient. Then you get 2x. So here, if this is 6.7 times 10 to the negative 5, and this one is 6.7 times 10 to the negative 5, because they're 1 to 1, again, because the equations are so simple, then all you have to do here is multiply this one by 2. Yes, you could write out the ratio, but that's all you would be doing. Okay, so now the only thing is when you do the KSP, make sure you write this step out here. You get marks for it. And because you want to remember, once it's a 2, yes, you get a 2x, but you also get an exponent of 2. I'm going to get a room there, sorry. Okay, 1.2 times 10 to the negative 12. All right, so this question says calculate the KSP of lead iodide dissolving in water if the concentration of lead ions is 0.0013. So this time it specifically says what the ion is, which is fine. Still cross out the solid. And then we can put this right down here. And then again, because that's a 2, we're going to do 2 times 0.0013. Okay, so again, streamline stoich a little bit. And then we have lead ions and iodide ions. And then don't forget the 2x, and then squared. This one, depending on what kind of calculator you have, you might get a different coefficient down here. It might actually say 8 times 10 to the negative 9. I have a calculator that will switch between scientific notation and standard form pretty easily, so I get more decimal places. If you don't get as many decimal places as me, don't worry about it, okay? You don't have to stress about that. Okay, so then the other type of question is calculating solubility. So basically this time now we are solving for x. Okay, so, and we're given the KSP. So similar to last section, there's really 2 kinds of questions, right? There's, are you given x, or do you have to solve for x? Okay, so same thing every time, solid on the left, split it apart into ions. But this time we are not given anything at equilibrium. We're given the KSP value. So we have to solve for x, which when you have an ion, the charge doesn't go above 3, right? So again, there really isn't a lot of variety here in the type of work you have to do, similar to last section with the quadratic formula. And you think, why do we have to use just the quadratic formula? That seems too easy. But there just isn't that much variety in the complexity of ionic compounds that we can do, right? So the same thing here. We have, once we plug in our numbers, we've got x and 2x squared. This is really as complicated as it can get, okay? So I'm going to show all my work here. Now, if you enjoy algebra, then perhaps you recognize that that already simplifies to 4x cubed, and you can certainly do that. 2x squared is 4x squared. So then when you have the same base, you add the exponents, so you get 4x cubed. Okay, so now what you need to do is divide by 4, and you have to divide by 4 first. Sorry, I don't know why it keeps doing that. I'm going to keep all the decimal places here. And you can certainly do this as one step. You can divide by 4 and then do the cubed root. and you should get the same answer as me. So to get rid of squared, you do the squared root. To get rid of cubed, you do the cubed root. And again, you really have to get to know your calculator and how you do the cubed root on there, because most calculators, are different. Okay, so the cubed root and again, if you're not doing scientific notation in your calculator correctly, then your calculator will do like the cubed root of the first number, but not the other numbers. So if you have a calculator that does scientific notation and you want to leave your answers like that, that's fine. If it doesn't, you don't need to. I don't really care. Okay, I'll accept either answer. All right, so that's really the two types of questions for this section. You just have to do your finding KSP, like these ones, when you're given the concentration at equilibrium, or you're not given the concentration, so that means you have to solve for X. So I'm going to post a worksheet called Solubility Equilibrium, and you're going to be working on topic number 1, which does have questions on the worksheet, and it also has a few textbook questions. And